Thank you very much, Dr. Sherp, and thank you very much for the panel for giving me this time. Uh, as usual, when I start by giving the tell me.
Yeah, I forgot the timing. So just try to finish within 30 minutes.
Within how much?
Within 30 minutes.
Yeah. I planned for 20 minutes.
Yeah, that's fine. Yeah.
All right. So, as usual, whenever we start with the presentation, I give the title and I'll try to break down the title into meaningful keywords to identify the themes of this research work. And lithium recovery from aqueous resources using sustainable solvents and solvent-based systems. That was the title. And without further ado, if I'm going to go throughout the keywords that we have in this title, we have starting by the end in mind, which is lithium recovery. And whether it's the laptop that I'm presenting with, or that's the one that you are seeing me through, the phones that we are using, or even with the electric vehicle boom, a lot of cars now are using the same technology, and this is the common factor that is being consumed by this technology, which is lithium-ion batteries, basically. So all of these daily commercial and daily practical uses of these devices, they include such technology. And even beyond that, beyond even the electric vehicle boom, now with the energy storage devices and the large-scale energy storage devices, they are also using lithium-ion storage technology. So we have everyone in terms of research practitioners, they know the value of lithium and they know that it's on the rise. So I'm not going to spend much time explaining how much it's being booming, but I want to just highlight why did I mention the batteries in the very beginning? Because I've been tracing the market the market trends in the USGS reports throughout the years, and I've been seeing that the battery percentage is being increased every year. So every year there's an increase in the uses of batteries for in terms of lithium. So lithium is the amount of lithium produced is distributed in different markets. However, every year we're seeing an increase in that batteries market, which is reflected in the daily life of the consumers in terms of, again, phones, laptops, cars, and so on and so forth. And that was the latest one in 2024, where the uses of lithium in batteries was up to 87%. That was the market share of batteries. At the same time, this important commodity is not distributed evenly throughout the world. So there is variations in that, where we have some kind of localities where they have rich amount of lithium, especially in Chile. We have in Australia as well, Argentina and China. So this kind of commodity is located in different locations, and with different kind of geographical locations, there is different sources where we can get lithium from. And the primary sources that I'm going to mention is the one that we are currently depending on, which is the one that we are, quote unquote, scarring the earth of, which is lithium mining from lithium-rich ores, where we are getting the rocks and then trying to get lithium out through different high pressure and high energy, like energy intensive processes. And we have the one that comes from saline brines, lithium extraction from saline brines, where we have also a rich amount of lithium that can be extracted and used for commercial purposes, which brings me to the next keyword, which is aqueous resources. And I'm going to go back again of why choosing aqueous resources for in particular. Now, when we're speaking about aqueous resources, it's not a straightforward, direct process, because you need to reduce the amount of volume that you have in such brines in order to be able to extract lithium in high quantities. You need to increase the concentration of lithium, and this process by itself takes months. So it's a long process, and even after waiting such amount period, or after that period, lithium is not the first to be extracted. you have a train of processes where you are removing, depending on the chemistry. I just put an example of a process, an example of flow diagram over there. But depending on the chemistry of the water, you are removing the magnesium, the nickel, and all of these different, the boron as well, all of these different kind of elements from the water, and you are left out with lithium, where you can either extract it through precipitation, absorption, and so on and so forth. So there's multiple kind of bottlenecks that you need to go through in order to get your lithium out, and still, because it's commercially lucrative, people are still doing it, and we need it actually in the market. And you've seen actually in a couple of years ago, I don't have the statistics here, I have it in a different presentation, where the lithium prices just went booming in fact in 2022. This is where you can see most of the lithium research articles were actually as well on the rise. So the money dictates this kind of research trends. Now it takes me to the second keyword, which is solvents. Now, when you are dealing with an aqueous phase, you can deal with it in different processes. But the process that I want to discuss here today is the one well-known, very mature, which is the solvent extraction process, or the liquid extraction process. Now, in a very, very simplistic kind of description, which is the one that we use in the batch mode in the lab, where you have an aqueous phase, and then let's assume that we have lithium ions, or we have some kind of contaminant here in that phase. And then you just mix it with an immiscible organic phase. And this organic phase is what we call the extractant, the one that has the affinity to grab lithium out of the water. And then you kind of put it into a certain period of time, and then you shake it, and the resulting is that the lithium is transported, is migrated from the aqueous phase to the organic phase through different processes as per each liquid. This is just a very generic example, but if you're going to take it into industrial scale, it's actually on the shape of a column where you have a liquid. You just, as you have an ion exchange column, you have a liquid extraction column where you have two phases forcing each other out, and they are separated based on density, based on affinity, and based on kind of different properties of the solvent itself. Which brings me to the second point. Now, if you're going to talk about solvents, if you want to extract lithium in a commercial scale, then you're going to use a lot of solvents, especially because you're dealing with a huge amount of water in terms of volume. So in that case, I want to just delve very quickly into a concept of the green chemistry and the 12 principles for green chemistry. These have been postulated in the late 1990s, I think by Paul Anastas. Where it's basically just a set of guidelines in order to maximize the efficiency and minimize the hazardous effects of the chemical uses that we are going through daily. Now, particularly from these 12 principles, I was looking at the waste prevention and the choices of solvents, where we are trying to choose different, safer, more environmentally friendly solvents. And since, again, we are dealing with a huge volume, you want to prevent such wastes and such leaching to the environment. That's nice so far. But if you look at the organic phases that we are using for the liquid extraction, you'll find a bunch of pirates in the back side of the bottle. And this is basically because we are using hazardous chemicals like kerosene or chloroform or carbon tetrachloride as the diluents or as the carrier solvents to carry out the extraction. That said, this takes me to the point of, well, what kind of green solvents, what kind of sustainable solvents are we talking about that can prevent this kind of issues? And I'm not in the business of dissing one solvent in terms of other. All of these examples, ionic liquids, supercritical fluids, and bio-based solvents, deep eutectic solvents, all of these work well in their own processes. There is advantages and disadvantages of each, and I have used different types of these green solvents, quote unquote green. because the term green itself depends in not only on the type of liquid, but on the material and the process, overall process, and so on and so forth. However, the most recent one of these solvents is deep eutectic solvents. And this is the one that I'm going to delve into a little bit in this research, where I'm kind of explaining what are the merits of such a solvent. Again, very briefly, you have a component A with a melting point A, and you have another component B with a melting point B. When you mix these two components at a particular ratio, you will end up with a component C with a melting point C. And that melting point is that eutectic point that we're talking about, where you are just mixing two components, not mixing with an external diluent, or not mixing, you just simply putting them together, and you're ending up with a liquid state solvent. Now, that said, what are those kind of key term, like the key term that I want to define this kind of solvent is that it's a mixture of components, as we just discussed. The components here maintain their own identity. We are not creating new solvents. We are not creating like a third solvent that is, or like a third material. It's not like the case of phynicals. It's not pseudo solvent. It's just a mixture of components where the components maintain their own identity, and they interact through each other with through hydrogen bonding. They interact with each other through hydrogen bonding, thus resulting in a melting point depression. And in addition to that one, we have, because we've changed the properties of these of these materials, we are ending up with unique properties. What kind of unique properties? Properties like high thermostability, low volatility, and in some cases we have biodegradability. And really the key point is as well is like the simplicity of synthesis, and in some cases as well you have the choice of pure renewable natural components, and there is even a different genre of DESs that's called natural DESs, because they purely use natural and renewable components. Components you'll find in your cup of tea, such as thymol, menthol, and sugars, diols, and stuff like that. So basically, it's a new type of designer solvent where you have the flexibility of mixing different components and getting new properties. That's the definition for DESs. And when we are looking at that process or that technology, the DESs, we are looking at a liquid extraction process, or the solvent extraction process I described earlier. And in that process, we're basically concerned of the basic properties that govern this process, which is we want to make sure that we have good extraction efficiency. We don't want the solvent itself to leach to the water. We don't want it to be soluble in water, and we want it to have some kind of desirable properties. Now, again, going back to the aqueous resources, it's not a case like. It's not one size fits all, it's a case by case. If you're looking at brines, you have high concentrations, 1 to 2 grams per liter. But if you're looking at seawater or even industrial water, you are looking at much more diluted levels of lithium. When I say diluted levels of lithium, it means a huge volume to be processed. In that case, and here's where I'm going to mention the different processes for lithium extraction. Solvent extraction is not the only one that can be used for recovering lithium. We have a bunch of processes, including solid liquid extraction processes, absorption, electrochemical processes, membranes, and as I said, it's not one size fits all. It's a case by case. Where you are choosing the right process for your stream, for your feed stream. In that sense, I wanted to explore how can we reduce the amount of solvents, of green solvent, because if I'm going to use DESs in a liquid state, I'm going to use a huge amount of volume. However, if I put it through one of these solid liquid extraction processes, I'm going to reduce the amount of volume, thus following the dream principles of chemistry. So that leaves me with the three keywords that I've been explaining in that title. We have the lithium resources, the choices of green solvents, in that case, deep eutectic solvents, and the processes that I want to integrate such solvents in. And from these processes, I was looking at solid liquid extraction processes, or in another terms, more simply stated, adsorption processes. If I'm looking at adsorption processes, I can just, if I work out the adsorption process, you can work out the solid liquid extraction process. And this takes me to the next key term, which is, or the next point in this presentation, which is, what is the research question that I'm trying to answer here? So we have the integration of three different, I would say, terms, or three different fields. We have the adsorption studies that we have in the literature. We have the green solvent studies for the DESs, and we have the studies done for lithium. Now, ideally, I would say, okay, look at the intersection of such fields of study, and then basically I would know exactly how are people, or how are other researchers or practitioners even doing this integration in terms of absorption, green solvents, DSs, and applying them for lithium. But not in my case. In my case, it was a little bit more interesting because you have to do PhD, you have to go through hard times. But I found
recording in progress.
Yeah, I found that some of the studies, they do integrate deep eutectic solvents with adsorption. However, none of them are applying them for lithium, or even very, very minimal research has been done on that field. We have a lot of studies, like tons of studies, doing absorption of lithium from different resources, and we have a lot of studies on the field of green solvents or DESs. Even our group previously have done that studies. But the intersection of green eutectic solvents used or adsorption, used within adsorption of lithium, that was something that needs to be investigated. And ideally, I wanted to look at the intersection of all three, but this research question is still pending. And in order to answer this research question, we needed to investigate the surrounding areas of that question. And we started in three parallel timelines. We started with, you see this alien in the intersection of these fields. That's going to be my thesis, probably. And we started with the integration of deep eutectic solvents for adsorption studies. And that was the first work that we wanted to understand this research question with. Basically, you sift through a lot of literature, you filter them out based on a specific criteria, which I'm going to explain now, and then you end up with the literature that you identified as something suitable for you to understand what's going on. And for that, I needed related papers only, something that has been, or some papers that are using DESs actually in a solid liquid extraction process, or in a variation of that solid liquid extraction process. At the same time, I wanted reliable papers that have done proper analysis for the developed DES-based adsorbents. And I didn't want any repetition, so I needed to identify clearly who's doing that DES-based adsorbent and for what. Anything beyond this criteria was actually excluded. And out of 600 plus papers, we were very, very kind of selective. And I got out of around 100, 140, 150, and then we kind of kept reducing until we had 127 papers, reliable papers that we can base our analysis or base our conclusions on. Of course, there is other reliable papers, but because the DES itself has been used before, so we did not include such papers. And then having just a sift through and a screening through these kind of papers, we identified where are they applying such quote unquote, I'm going to call them green adsorbents or DES integrated adsorbents, something like this. So where are they applying those DES-based adsorbents? You can see that a huge portion, like the vast majority of those applications were actually in the field of water and wastewater treatment. Yes, we have some applications in protein isolation, especially because proteins have different kind of structures, and you need to kind of tailor-made particular adsorbents for such extraction processes. You have extraction from food, extraction from biomass, some medical applications, and the vast majority, as I said, was from the water and wastewater treatment applications. Fair enough. And from these water treatment applications, we had a significant amount in dye adsorption. Actually, the majority was from dye adsorption, absorbing different dyes, anionic dyes and cationic dyes from water, heavy metals, some pharmaceuticals, and some phenols and other polyaromatic hydrocarbons. All right. So after identifying where these DES-based adsorbents are being used, we want to identify what are the materials that are being used for such applications. And then looking at all of these materials that have been used, because especially in material science, you can just mix and match different materials in order to achieve a particular objective. And we have seen that there is a plethora of hybridization between different chemicals. You have carbon nanotubes, graphene oxide, some metal oxides, MOFs, chitosan, bio-based adsorbents, molecularly imprinted polymers. But I want you just to mention what's going on exactly with this graph, because the analysis was not just like a plain vanilla. We went a little bit deeper to identify exactly what's going on with the trend. For example, you'll see here that around 8.8%, almost like 10% of the studies are using carbon nanotubes. And if you look at the percentage of hybridization or the percentage of using carbon nanotubes with other components, you'll find that it's very minimal. Like only a couple of studies have used carbon nanotubes with metal oxides and with other components. However, the majority were just using CNTs as standalone, of course, CNTs with DESs. However, if you dig a little bit deeper, you'll find that most of these studies are done with the same exact research group from the same exact people. Thus, they are most likely following the same exact methodology they are doing instead of trying different methodologies for CNTs. So this kind of critical feedback was actually taken into consideration while building such kind of graphs and such kind of understanding of the field and understanding of the research question. Likewise, when we go for the uses of ferric oxide, usually you can see ferric oxide is used as an additive material to introduce magnetic properties. That's why you find it's very, like, I think it's only used alone once or twice, but most of the time it's used with other components in order to introduce such magnetic property and enhance the separation process after extraction. But these kind of trends were also highlighted. And when a specific category is increased, in that case, we kind of digged in a little bit deeper to understand what's going on with that field, and then we identified where is these applications going through. You'll find that the majority of ferric oxide studies are going through MIPs as well, because MIPs as a standalone, perhaps there's a difficulty in separating them. That's why most of these studies have been used to introduce ferric oxide and ease the solid liquid extraction process or back extraction process. Likewise, if you trace what are the DES used you'll find a different trend. And then if you look at the targets and the applications and so on and so forth, so we've kind of dissected each of these categories in order to understand which material is used for which type of target. Now, after having studied the base materials, we wanted to understand what are the researchers using for DESs. And as you may remember, DESs are used either as with component A and component B, or even more than one component, more than two components. It could be used for three components as well. You can see the majority of hydrogen bond acceptors, or the first component, is using choline chloride. It's one of the, you can say, legacy hydrogen base. It's actually the first chemical that have been used to introduce DESs back in 2001. You'll find some other variations of ammonium and phosphonium salts, and you have some other metal salts. If you look at the hydrogen bond donor, you'll find the majority are using ethylene glycol, glycerol, or urea, these three, with other uses of organic acids and methyl acrylate. Again, we did not take things at face value. We looked at why are they using such components. And the thing is, people from the adsorption industry have been borrowing from the DES field as it is. So they have the majority of choline chloride and ethylene glycol, glycerol, urea, these combinations is actually a very well studied DES that has been there for some time. And people have been just borrowing it off the shelf and using it for different applications. There's nothing wrong with that. However, it still doesn't answer the question of why are you using this particular DES for this particular application. Some people have answered, some people, or the majority of articles, did not answer that question, and they just claim that because it's a green solvent, we are using it. However, this is not a justifiable kind of cause to use a particular solvent because it might not be working well for that particular application. After having this bird view of what's going on with this intersection with both fields, we've noticed that we want to answer the question of how. How are you preparing such solvents? Now, we already had a lot of question marks from that bird view. We had even more question marks when we traced how are they synthesizing such solvents? Because as you remember in the definition that I mentioned, it's not new solvent. It's a mixture of solvents maintaining their own identity. So after looking at the methodologies in these 100 plus papers and even more, we've seen the good, the bad, and the ugly. And again, I'm not trying to diss, or I'm not trying to kind of say something bad about the literature, but people are taking the pragmatic results of mixing two things together and having something like working or pragmatically working, and then publishing it based on such results. However, if you look at the how, like why are you preparing and how are you preparing some solvents, we found that first, they are claiming a lot of methodologies. When you trace them back, they're actually traced into only three methods. Either you are mixing your DES solvent with your adsorbent in a kind of reaction, or or for example with ethanol, methanol, or even DI water, and then you are claiming that the DES has been functionalized with the adsorbent material, or you are actually throwing in the adsorbent material in a DES and then you are heating and shaking, where you are also claiming that the DES has been functionalized onto the adsorbent material in a particular percentage. And the last method was actually just solvothermal methods, where you're actually throwing in the DES materials in an autoclave or in a kind of closed-in reaction, and you are heating to a high temperature where you are carbonizing or kind of synthesizing the adsorbent material. A lot of questions were risen up in this kind of scheme. how can you maintain the DES properties if you are diluting them? And if you are mixing the DES with the adsorbent material, how can you make sure that the stability of the DES onto the adsorbent is maintained? And especially for the third one, how are you ensuring that if you are heating up to 600 or 400 degrees, you are most probably, or actually you are degrading the DES components. They are just simple components, sugars and salts. They cannot maintain such high temperature. All of these questions, after giving them a thorough look in the literature and in the field and in the chemistry of DESs, we had to postulate, or we postulated a framework where you can actually apply DESs within the absorption field. And this framework was actually starting with determining the objective, which brings me back to the earlier point: why are you using the DES in the beginning, in the first place? If you can answer this question, you can choose the actual components of your DES, and then you can choose the roles and the functions of this DES. For example, if I want a hydrophobic DES, I would most probably choose a hydrophobic component in order to introduce this kind of functionality. So if it's serving the function, then that's good. If it's not, then you're going to have to resort back to your material selection and change your choices. If it's serving a function, then you have to go and test if it's functionalizable. Can you functionalize such components into your DES? Yes, then you can go ahead and you can test. Are they forming a DES? Because if they are not forming a DES, then why would you choose them, or why would you want to use them? You can just use the components on their own. If you pass throughout all of these filters, and then after forming the DES, if it's serving the objective that you started with, then you have the chance now to go through the adsorption preparation. Now you can prepare an adsorbent based on the DES that you have selected. And the preparation of the adsorbent itself requires from you to identify what kind of route of synthesis they want to use, the one out of three that we have described earlier. But at the same time, I have put two parallel routes over here, because if you are trying to achieve a particular objective from your adsorbent, and if one of the components of the DES can provide this function, then why would you add the second components? What's the use of adding more material and more components if you can do it with one component? Yes, you're going to have to let go of the idea of having a DES, but at least you are saving on some materials. You're still using a green kind of concept, which is using one material, one green material instead of two. And then you're going to test if it can be functionalized or synthesized, go through the characterization processes, and then if it is successfully incorporated, you can go through the analysis. In parallel, you can also prepare the DES and go through the same exact route and see exactly what's the difference between using your components on their own versus using the DES. And yes, there is some synergy that can be added to the DES, and here's where the fruit of using DESs lies in. This is because you are integrating different components and having that synergetic effect. And without going through this kind of step-by-step, bottom-up approach, you will not be able to harness this kind of, I would say, merit or property of DESs. Yes, you will get a pragmatic result where you are achieving whatever objective you are trying to achieve, but you are not understanding what's going on with that particular chemistry or with that particular process. And thus, you will not be able to enhance that efficiency later on. So that scheme was postulated before going to that postulation. The data itself, the huge amount of graphs and data was actually built after properly sorting out this kind of literature search and making it available where you can have an interactive kind of user-friendly Excel sheet where you can sort out and see exactly at which year who's doing what and what kind of material are being used for what kind of DES, and what kind of targets have been used, have been targeted for a particular process, and so on and so forth. That was all the output of this kind of step of investigation, I would call it, in the aim of answering that research question was a comprehensive critical literature review. I think around 40,000 words were written in describing and critiquing the merger of both fields, an accessible user-friendly database, and the output was published in Progress in Material Science. Finally, actually, it took some time in order to put all of these things into one kind of work. Moving swiftly forward and back to our alien, once we have understood, hopefully, that the intersection of absorption and green solvents, we wanted to see exactly what's going on with the second intersection, which is the one with green solvents and lithium. How are they using deep eutectic solvents for lithium extraction? Now, after going through a different set of literature, we went through the solvent design process first. As I mentioned previously in the definition of DSS, you choose a component A and a component B, and then basically at a particular ratio, you are getting the eutectic point, or that depression in the melting point. Now, we can do that at an issue using some kind of thermodynamics equations, but this is just a rule of thumb where you can just having a general idea of where is that eutectic point happening before going for experimental validation or experimental synthesis. This is just a step we use in order to reduce the amount of experimental runs. There is even more advanced equations and advanced methods that can be used. Now, one thing that I want to note here, that the solvent design was not arbitrary at all. It was actually based on another comprehensive review that we are currently working on, where we have already collected a huge amount of data points about who's using what DESs for lithium extraction. But that could come later on. So we have designed, or we have kind of screened different components in the solvent design process, and we built the solid liquid phase equilibria. This is the SLA diagram, where we can kind of have a rough idea of where is that eutectic point happening, so that we can prepare the DES accordingly. And this is exactly what we did. So the preparation of the DES is, again, as I mentioned, one of the properties of DES is the simplicity of synthesis. You just mix the components together at a particular temperature, like usually 70 or 80, and you shake them for a period of time, and then the resulting is a different sets of DESs that can be used for your extraction. So we started with testing such particular solvents and to see their efficiency in lithium extraction. Now, just to explain exactly what I mean by TTFA, thymol is the one that I showed earlier. Menthol is also the mint that we use in our tea, lauric acid, and then the TTFA and the TBFA are actually dibeta ketones that are used for lithium extraction. In the literature, and even in the late 1980s, they have been reported that to form a particular coordination with lithium ions in water. So we have resorted to testing these components, and we looked at that extraction efficiency at two different feed streams. We wanted to understand the effect of pH. So we used lithium chloride and lithium hydroxide, where lithium chloride is basically neutral, pH neutral, so the pH is around 7, and we have lithium hydroxide where we have the pH is around 12.2, something like this. And as expected, we did not find any extraction for all 4 DESs from lithium chloride solution. However, we found significant extraction for lithium hydroxide solution. It's just a plain solution. There is no competing ions. We just want to understand the behavior of the DESs with lithium ions. 100 ppm, that's the concentration that we used. And then moving forward, we wanted to understand because this particular combination had been mentioned in the literature, so we tried to make different new combinations based on that one. So these combinations gave some kind of extraction efficiency, and I wanted to know exactly. Okay, I have 5 more minutes.
Can you wrap up in 2 minutes?
Yeah, I can wrap up in. Yes, I can wrap up in 2 minutes, no worries. So we want to understand exactly what is the effect of the solvent without the extractant. So we run a lot of different binary combinations in order to find the effect, the pure effect of each component on itself. You can see that thymol menthol on itself doesn't have any extraction efficiency. However, when you combine it with different components, you do have a particular extraction efficiency. And that was the case with other binary combinations. We compared them all together in order to identify which components can work for our case for lithium extraction. Of course, we used previous combinations to compare previously reported combinations, and then we modified them later on in our own method with ternary DESs. So we chose different ternary DESs as well, and we played around with them in order to see how can we enhance, you can say, the extraction efficiency. Of course, we faced some difficulties here where we actually decreased the extraction efficiency, and that was actually due to the purity of the additive that we used. So we have to check the purity properly. So that was the initial works that we did in that first stage, where we have identified possible research gaps and then traced the different trajectories within the intersection of both fields of DES and absorption, ending up with postulating our own methodological framework where we can use it later on for the development of DES-based absorption, and ending starting the experimental phase where we are testing novel combinations for DESs for lithium extraction. Now, this is the trajectory that I'm following so far, and continuing on is going to be on understanding those intersection points until we finally reach out the focal point of the intersection of all three for lithium extraction. That's what I have for the presentations. For the recommendations, I'm actually leaving it for the people that have been listening to me for the past 30 minutes. And thank you very much.